the title that we have decided together is the from concept to implementation, and we discuss about CTO programs and the guide wire algorithm, which is a crucial topic in order to have the good success in the procedure that we do. And in order to do that, the session is built as with 3 lectures. The first one will be provided by Mr. Falto, and who's going to talk about how to build a strong foundation and how to establish a good CTO program from a specific point of view, which is the point of view of our nurses and our technicians, which are fundamental in order to have good results and to have everything set up in a good fashion in order to start. And then we're going to move to the presentation of Dr. Bagnal, and who's going to give you an overview of the anatomy and the features of the wires that we use to have our procedure. And then we talk about a little bit about algorithm and how to use the concept that we already have discussed in the previous 2 lectures. Before starting, let me just remind you that interaction with you is strongly desired by all of us, and the way to interact with the question and comments and whatever is the part of the question and answer that you have on the bottom part of the bar of your Zoom window in your Zoom presentation. So just type the question that you want to give, or the comment that you want to give, and then maybe at the end of the 3 presentation we can share with the other people, and we can have some sort of discussion about that. So stop about talking about the general rules of the webinar, and we can move to the first lecture, which will be given by Mr. Falto. We will talk about building a strong foundation, steps to establish a CTO program in our CAT labs. So I stop my sharing. I leave you the floor, and I leave you the word. Mr. Falto.
Okay, thank you very much, Dr. Gagnon, for this introduction. Thanks to, can you see my screen? It's okay for you? Okay.
Yes, perfect.
Thanks to Asahi Company for this invitation. And it's a big pleasure to be with you this afternoon for this webinar. And I'm going to try to share my experience and as a technician of the CAT lab, and how I build up, how to set up my experience in the CTO program. So just one slide to introduce myself. I am in interventional cardiology since so many years. In my center is in the northeast of France, in Colmar. 2 CAT labs in my hospital. 1,200 PCI last year, around 50 CTO. So I'm a technician or radiographer if you want, and also I'm the CAT lab manager. I also be part of the MLCTO committee. The MLCTO is a big congress of CTO in France, and I am in charge of the paramedics sessions. So to begin the session, I would like to precise that the CTO, it's a very specific area. CTO, chronic total occlusion, with a strict definition, no flow, a TIMI flow 0, with an occlusion that dates back at least 3 months. And sometimes you can have this kind of image in your run. And if it's a STEMI or a CTO, you will not be in the same context. Can have the same image, but not the same context. A specific area, and our doctors, they know it, but the different techniques, different materials, specific techniques by the integrated approach, by true-to-true lumen, by the dissection re-enter. And we know that the guide wire, when you are in the false lumen, it's difficult to re-enter. And you are going to explain us how you do it. And when it's not possible by the integrated approach, you can have the retrograde approach, which is something completely different like the other approach of the other lesion. The selection of our patient is very important. If the patient is symptomatic, the indication is clear. But when the patient is not symptomatic, you have to prove the schema of the territory CTO, which must be more than 10%. And for each CTO, you have to balance the benefits, better quality of life, less dyspnea, less angina, with the risk of possible complications. So you begin your program, how can you be prepared? I think you have to be interested, in fact, in the CTO. You have to be interested about the CTO lesion to understand the histopathology, which is not the same like the other lesions. The presence of a microchannels you don't see at the angiogram. You have to see the nature of the caps, proximal or distal, or when you look in the body of your CTO and when you see lots of calcification, you know that the strategy or the material which will be used are not the same. Different aspects like the bridging or development of the collateral is also important. Increase your knowledge, some books to read or to download, so in order to become familiar with the different terms. What is the proximal cap? What is a reverse cut? Different tools you are going to discover and which are going to help you to perform your procedure. At the end, you are going to understand why CTO PCI is so different than your PCI in your daily routine. Participate also to different meetings, and the ML-CTO in France, it's a big event, you know it, at the end of June. You can also participate through different live course platform in CatLab is very developed about that. I developed in France a specific website for French technicians, and nurses, in which I developed the CTO part in order for all the nurses, all the technicians to increase their knowledge. And I think when you begin the CTO, it's important to discuss with your operator to analyze the angiogram. And then you are going to discuss with him for which kind of a CTO, what can be the strategies. What is your plan? What is your first plan? Are you going to integrate, or do we need a dual injection because you are going to move to the retrograde approach? It's very difficult. You begin the session, the CTO program, it's very difficult. The question is, do we need a proctor to help you in order to achieve the procedure? I think it's important to know also the GCTO score, which is a score of complexity based on the anatomy. 5 points based on the anatomy. The first about the cap, when the cap is ambiguous, when it's not clear, 1 point. When you see calcification, 1 point. The tortuosity, 1 point. When it's long, more than 20 millimeters, it's considered that long, so 1 point. And when it's a second attempt, it's also 1 point. So more you will have point, more it will be difficult. And that's why I think at the beginning of the program, you have to begin the program with a GCTO score 0 or 1. About the patient. 2 years after the beginning of my procedure, I observed that the average time of the CTO procedure is around 90 minutes. So for me, it's a long procedure, it's complex, it's long. And when it's long, you will have an impact of your patient. First, the comfort of the patient. The patient must be relaxed. He must be warned about the length of the examination. And you need his cooperation for your success. Second impact, the volume of contrast. And you need to consider the contrast-induced acute kidney injuries. Third impact is the radiation. And then you have to optimize and to limit the radiation of the patient. More you are going to optimize the radiation, more the operator will have the time to open the CTO. And that is very, very important. the last impact is the coagulation management with the ACT protocol to cut off 300 seconds when you are in the antegrade, 350 when you are in the retrograde approach. And you have to verify with ACT every 30 minutes. It depends the center, but in my center, every 30 minutes, we have to check to verify the score. The 4-axis must be prepared, the 2 radial, the 2 femoral, because sometimes you have to switch during the procedure. So prepare the 4-axis. The monitoring will be, I will say, classic, but we have to add another pressure line when you have a dual injection. If you have double access, you need 2 pressure lines. It's very important also. You need the consent of your patient, and you have to inform him about the length of the procedure. Be careful, it will be long, are you relaxed? You need to explain, to inform him about 2-axis, which is something different from another PCI, and why not the limits of the CTO, the limits with the contrast or the radiation. And also, why not to inform him about the possible failure. It's possible, it's not possible today, but we are going to try. The procedure. In my center, I set up a specific CTO checklist in order to not forget any details for all the team, all the paramedic team to before and during the CTO. I also draw the CTO on a paper on the board to explain the CTO, the different material, and why not the different strategies you are going to use. Build your toolbox. It's very important. If you have no tools, it's not possible to achieve your CTO. You need tools. Tools are mandatory. Wires, and we are going to talk about that during this webinar. And of course, Asahi family wires, which is very, very important in our cath lab. Microcatheters, guiding, etc. Lot of specific tools you need for your CTO. And when you are going to be interested by all the CTO tools, they are going to help you in your daily complex lesions. So guiding catheter, microcatheter, anchoring if necessary, etc. This is my toolbox, and one on my box, you see all the Asahi wires. And the question is, which wire for which CTO? And then when you can answer this question, you will master the situation. But it's very difficult. That's why with Stéphane Duvezin last year and Julie, we organized a webinar for the text and nurse in France, dedicated to the guide wire to explain the different properties, the different way to use the different guide wires. For the organization, 2 cath labs preferably, it's possible in your center, but the goal is to not disturb the operator by a STEMI. It's not possible to be in your CTO and with a STEMI before your door. It's not possible. You have to be concentrated in your CTO. So if it's possible to have 2 rooms, that's why in my activity, I shared my activity with EP, vascular structure. I need the Wednesday day. It's the best day for me to manage the CTO because I have 2 cath labs. And if you're paramedics and you assist your operator, it's not possible to have this kind of table. You are going to have lots of devices on your table. You have to be organized. One side, the wires, in the middle, balloon, on the other side, the stents, lots of devices you are going to use. And the operators are going to need the same wires used 10 minutes before, again. So you have to be very organized. About the complication, you need to know that, for instance, the rate of perforation is a little bit higher in CTO than in conventional PCI. When I look at the meta-analysis, 2.9 versus 0.2 when it's not a CTO. So you have to keep in your mind this kind of number of statistics. So you must be prepared. Covered stents, the coils, you need to be prepared for an eventual complications. Ask the second physicians to check the situation by the echo and prepare, if necessary, the pericardial drainage set. I like this slide from Manos Brilakis, who said that more you are going to do CTO, more you will have success and less you will have misses. I think it's very important to have that in your mind. So higher your CTO will be important, your volume is important, lower will be your complications. Take a message to say that to set up a CTO program in your cath lab is it's a challenge, but not only for you, for physicians, but also for us paramedics. So for all the staff, it's important to call a proctor when the procedure is too difficult or when it's a second attempt to increase your rate of success and to avoid complications. You have seen it, organization, education, CTO is time consuming. And at the beginning of your procedure of your program, the most difficulties when you manage the cath lab is to convince your team. And that's why I think it's important to have the follow-up of patient, and we control the CTO between 6 and 9 months after the procedure. And if you can, ask a CTO companion to set up your program in your center or in his center to increase your knowledge, to develop, in order to develop, to help develop your program. Just one slide about DML CTO meeting. You know, this meeting, a great meeting in Europe or in France at the end of June, and I manage the paramedic session. So if you are interested, register, reserve your seat. It's paramedic sessions for 2 full days, from theory to practice. We assist to the all life cases with my master, and I have the support of my master of the CTO, Alexandre Avron, Cambis, and Stéphane Raffray. They support my paramedic session, and it's a very pleasure to organize the program about the CTO. So thanks for this, for your attention. I give you my address email if you will have any question. Don't hesitate. And so thanks for your attention. I will stop to share my screen, Dr. Gagnon.
So thank you very much. It's been a beautiful overview and beautiful show of how it works in real life in our cath labs. Yeah. Before moving to the next presentation, I would just like to ask you a short question, and then maybe we have the longest part of the discussion at the end. You have said that when we talk about, we use a lot of contrast, a lot of radiation, and maybe the same concept is about complication, but we can save it for later. Yeah. We say something which is based on very old data. What's the reality in your cath lab? I mean, do you think that it's still the same concept that we had 5 or 6 or 10 years ago when we started collecting data, or maybe now we're using a lower amount of radiation than for a conventional PCI 10 years ago?
Yes, it will nowadays it will be less that at the beginning of the program, and it's a good news for the patient, but sometimes it's also difficult, and I would like to say that you have to be careful about that, even if the data are so old for you, but now you have the IVUS guided with no contrast. Okay, you are going to help you in that, but you need contrast, you need radiation, and at the moment you have to be careful with that. So you have to say, Dr. Gagnon, it's 300 cc volume. What are we going to do now? Or Dr. Bagnell, I said, so we have 5 grays. Well, what are we going? You are not, it's not, you don't cross the lesion. What are we going now? I just would like to say that keep in your mind that it's a limit. It can be a limit of the CTO. even if you are now so involved in the wires and in the material, but you have lots of young cardiologists who begin the CTO program. And when you begin the CTO program, I think it's important to have in your mind that you can have some limits, which can be the radiation and the contrast.
Maybe also good news is the fact that as we are very dedicated and we are very concerned about radiation and contrast, we are able to reduce the radiation and the contrast even in conventional PCI. So now it's very infrequent to have a PCI which is a CTO PCI which is more than 200 cc of contrast and more than 1.5 grams of radiation at the end of the day. And so, and also the same amount of reduction is you can see on the conventional PCI. So it's very important to be dedicated and focused on the topic. So thank
and
you.
Have, excuse me, doctor, and you have the paramedics teams. It's their role to warn you about the situation, the length of the examination, the contrast. So it's also the role of the paramedics teams.
Yeah, definitely. I would like also to talk with you about the fact that you have to share with all the people in the cath lab when you start performing a PCI, but maybe we can do it later, and then we can move to the second lecture given by Dr. Bagnal, who's gonna talk about unlocking the power of the guide wires and an introduction to the anatomy and to the feature of these wonderful devices. So.
Great. Many thanks, everyone, for coming along to this great talk today. And thank you very much to Asahi for sponsoring this. Can everybody see the slide okay?
Yep.
It's okay.
So we're going to talk today about guide wires. We heard how finding the right tool for the right lesion is all important to achieve success. So it may surprise you to hear that there are over 300 different guide wires on the market today. So it's a very confusing environment to know what to choose. And guide wires are absolutely essential. You can't do anything in angioplasty unless you have a wire across your lesion to be able to deliver your equipment, deliver your stent, and make the patient better. And that's even more the case in CTO PCI, where the wire characteristics that you choose can be the difference between crossing that lesion or not. So, the million-dollar question, how do you choose the right wire? Well, the key is about understanding the task at hand, understanding the lesion. That comes from good and careful, detailed analysis of the angiogram first off. The second part of the equation is to understand the properties of your tools that you're going to use. And this doesn't come for free. This involves investment from you into learning this. And what we're going to talk about today is how different guide wires are like different tools. So in your toolbox at home, you may have a saw, you may have a hammer, and you need to understand what the properties of those are. Otherwise, you might find yourself using a hammer to try and cut a piece of wood or using a saw to knock in a nail, and neither of those are going to be successful. So if you understand the problem, you choose the right tool, that puts you on the pathway to success. I'll give you another analogy. This is my imaginary fantasy garage at home. Okay, now I think you can probably all guess which is my favorite car on here. And most of us, by now, will have a favorite guide wire. Okay, but these cars, these are tools. These are just like the tools of our guide wires. Now, I've been lucky enough to be given a track day. I can go and drive my favorite red shiny sports car at the track day. Okay, sounds great. But I've got a few things to do first. I live in the countryside and I'm not going to be able to get my Ferrari across this field. So I need a different solution for this type of problem. My wife's told me that the kids need picking up from school before I can go and enjoy my fun at the track. And this is going to take me 4 times as long if I've only got a 2-seater car. So if I'm going to use my favorite car here, I need to be able to get to this situation first. My Ferrari is only going to be great in this situation and it's going to be pretty inadequate for lots of the other situations. So think of your wires like tools, very specific tools for very specific purposes. And in CTOs, it is rarely one wire for the whole case. And that's because you will encounter a different problem when you're approaching the proximal cap, a different problem to get through the proximal cap, and a different problem when you arrive at the distal cap, and then another problem when you've got through that and are trying to deliver equipment. So you may need completely different solutions for each of those different situations. So to approach our understanding of what wire is required for which particular part of the case, we need to understand what's in a wire. What are the elements of it? And how do those different elements contribute to the function of that tool? So let's talk about basic wire construction. All wires are made up of a core, and that core is typically stainless steel. Around that core is then wrapped a series of coils. These coils are a piece of wire which is just wrapped sequentially around the wire. And those coils provide flexibility and they provide feel. And then finally, in some wires, a coating is put over the top of those coils, again to affect how the feel and the slip of the wire across a lesion. So we have coatings, we have cores, we have coils. One other feature is called the tip load, which is how stiff the wire is, how much it bends when you push on it. And together they contribute to determining the function of the wire and how it feels when it's in your hands and when you're engaging that wire with your lesion. Sorry, engaging the lesion with your wire. So let's take each of those in turn. Wire cores. The first difference that we see between different wires is in their thickness. So a wire which is of wider diameter, for example, like a Grand Slam wire, will give you more support. So that gives you more ability to deliver equipment, particularly around bends. A wire, conversely, with a smaller diameter gives you more flexibility. So that wire may be able to go round bends better. We then take a look at how that wire core is tapered. The Grand Slam has a short taper to it. And that means, again, it supplies more support because more of the length of the wire is made up of thick wire. So there's more of it giving you support. In contrast, in the Xeon wire, there's a much longer taper to the tip of the wire, and that provides more flexibility of that tip and makes that tip less traumatic. So we can see here, again, the coils that you can put on the outside of a wire. Something like the Xeon has a long segment of coils, 28 centimeters long. So that gives that tip lots of flexibility, particularly when combined with that long taper that we've just described. The other side of the coin is a wire which has a much shorter coil segment. So when you put all these things together, you can test this out in the lab. And when you put all these things together, you can see very clear differences for the wires. This is just a machine that Asahi will use where you hold up the wire at one end and look at the flexibility of it. So you can see that something like the Grand Slam is able to support itself because it's made of a thick diameter wire. It has a short taper. It has a short spring coil length. The Xeon, on the other hand, much thinner, longer taper, longer coil segment, and you can see that it hangs much further down because it just hasn't got as much support to it, but is much more flexible as a result. So let's talk about outside diameters of the coils and wires because they also affect its function. When we're moving a wire down a coronary artery, if that wire is very sharp and pointed, it is very likely to get stuck in the wall. Sometimes that can be something that we want to achieve, but most of the time it's not. So a tapered wire is more likely to cause trauma to a vessel. but a wire with coils is more likely to be atraumatic. So, and a wire that isn't tapered, again, has less propensity to want to stick into the wall. So that's been designed into wires, and we have wires like the cyan blue, which is a normal 0.014 inch wire, but we have specifically designed wires which have tapered tips. These are things like the Confianza brands of wires. Now, we don't do that to make them more dangerous, but we do that because we have certain situations where we deliberately need to have extra point force to push through things. And this is particularly the case when you come to the proximal and the distal cap of your CTO. So those are useful wires to use in those positions. But conversely, like my Ferrari, it's not very good elsewhere because it then becomes a more dangerous wire to use when you're in the normal distal vessel. So here's an example of the different effects that tapering has. On the left-hand side, you can see that tapering the wire increases the amount of point force. And if this was your skin at the bottom here, you'd feel it pretty painful if that sharp pencil was pointing into you. Flip the pencil round like the cyan with a nice broad end to it, nice and atraumatic. Now we can, as I say, increase the amount of point force by doing things like tapering the tip, but also we spoke earlier about that core thickness, and that gives you the tip force of the wire. We talked about this thing called the tip load, and you may have heard that and seen it on the outside of the packages of your wires, and the different wires come with different tip loads. So this is what we mean when we're talking about tip loads. It's a very simple concept. Essentially, you push on the wire, and the amount of force it takes in grams for the wire to bend is the tip load of the wire. Putting that into a practical perspective, when you're performing an angioplasty procedure and you're moving your wire down a vessel, if you see the tip buckle over on a 1 gram wire, you're exerting 1 gram of force, more than 1 gram of force at that tip. If you took a wire with a 12 gram tip load, it wouldn't bend over like that. You would have to be exerting more than 12 grams of tip for it to bend over. Okay, so this is really important for the visual feedback of the wires, to understand your tip load and to how much force you're putting in, because some wires only you're getting visual feedback and not so much a feel feedback. And there are a whole range of tip loads. I've just put a few of the Asahi ones on this one, but you can have tip loads that go from cyan blue, which is 0.5 gram, up to 18, 20 grams, etc. So there are vast ranges of differences. And obviously ones which have more tip force, allowing you to put more push behind the wire before it bends over, gives you much more penetrative power, which is useful in certain situations and very dangerous in others. But you can also manipulate your tip load on your wire by your microcatheter. And most people will be using microcatheters during CTO procedures because there's rarely one wire that's good for the whole case. And microcatheters are a way of exchanging your wires without losing the ground that you've already covered. But if you take something like a Fielder XT, which is a low tip load wire, 0.8 grams before it starts to bend, if you move a microcatheter closer to the tip of that wire, you can get that tip load to increase to up to 3 grams. So it can completely change it. And sometimes if your wire is bending over when you're trying to engage a proximal cap, simply bringing the microcatheter closer to the tip can be one way of providing enough tip force to penetrate through. You should be aware as well that when you're going through a CTO lesion, that the same effect can occur, because obviously the wire is constrained then by the plaque material, and that can increase the effective tip load. Let's talk about coatings next. Coatings come in 3 general types. And what we're doing here is, like most things in engineering, we are balancing one attribute against another. You give with one hand, you take away with the other. So the types of coatings that you have vary from, on the one extreme, a hydrophobic coating, to on the other extreme, a polymer jacket, which is a very hydrophilic, slippery coating. The hydrophobic coatings grip, and so they give you feel and tactile feel. On the other hand, the polymer jacketed wires are designed to slip over things, so you don't get any tactile feel. So you have to become increasingly aware of the visual feedback that you're getting for where your wire position is, because you will not feel when you're about to go out the end of the vessel, or if you're to move into the subintimal space in the same way with a polymer jacketed wire as you would with a hydrophobic coated wire. So here are the different types. Hydrophobic wires, their coatings, they produce a waxy-like feel when they become wet in the blood. So lots of tactile feedback, less visual feedback. Hydrophilic ones become gel-like when they are wet, so they tend to slide better over lesions and through vessels. You can mix and match those on those. So you can have parts of your wire that have a waxy coating, part that have a gel-like coating, giving this hybrid coating, so you get tactile feedback at the tip, but a hydrophilic slip performance further back once you've crossed that area. And finally, as we said, polymer jackets. These are very lubricious, very gel-like and smooth, designed to have as much slip as possible. And this enables wires with polymer jackets to track and slide through tortuous vessels, across gritty, calcified lesions, and also to go through microchannels and help disperse tissue as you move through a CTO segment. And this is what they look like up close. And you can see suddenly when you talk about polymer jackets, what a difference it looks like. You've got the kind of ribbed, rigid one of the uncoated wire at the top, and you basically dip that in some molten plastic and put a polymer coat on it to make it smooth, slippery, and able to go through lesions very easily, but at the same time you lose your tactile feedback as a consequence of that. Final element I want to talk about is tip design. So wires all come with a tip on them. This is the bit that leads. The conventional guide wires come with a ball-like tip, again, to kind of make it atraumatic. But Asahi have also got a specially designed microcone tip, which has a point to it to further enhance those wires that have got some tapering to them that enable penetration, should you require that. And again, this is how they might look underneath a microscope. And you can see that there's really quite a difference between these. So the one on the left, this would be like your Gaia families of wires, that have got a tapered cone like this. So let's have a look at how wire technology comes together, because we've looked at the individual elements now. So in the 20th century, we had core to tip design. They introduced shaping ribbons, which are these small areas here, an extra sort of segment of wire that allows you to get a very specific shape on the wire when you bend it, and for that shape to be retained when you move through lesions, or if you bash against the wall when you draw, you've still got the same curve on it. The Asahi wires have gone to another level on this. They've got something called the composite core, which I've got an animation to show you in just a moment. And this is something that takes the technology that we've seen there from before, shaping ribbons, core to tip designs, but adds in other elements, which I shall show you in a second, to give you really fantastic steerability and whilst maintaining flexibility and trackability. So you'll see on the picture on the right, the additional elements that come in. There's a twist wire, there's a rope coil wire, there's an outer coil. And this is how the devices are put together. First off here, we've got our rope coil. And inserted into that rope coil, we have our core wire, which has another twist wire next to it. And then finally, we have our spring coils, which go over the top of that. And then onto the end of that goes your nose cone. So it's an incredibly complicated piece of engineering, these wires. So as you're bending them and twisting them and knuckling them, you can imagine some poor engineer who spent their lifetime designing the intricacies of all this, just gently crying. But they are fantastic pieces of technology, and when you understand what goes into them and how you can manipulate those different elements to change the properties of the tool, then you can really come to master the complexities of CTO lesions. The effect of all these different elements is to change how a wire torques. You'll probably all be familiar with what we see on the wire on the top of our screen now, which is this kind of whipping type of action. As you turn, the torque builds up, the wire tip doesn't move, and then suddenly it all moves all in one go. The Asahi technology is there to allow us to have a continuous one-to-one rotation so you can very accurately steer your wire. So I hope what you've seen from this talk today is how things like the coatings, the core, the coils, the different types of tip load all come together for one particular wire to produce its function, to determine its function, and to determine how it feels in your hands. So we're moving away from that idea of having a favorite wire, the one that your boss used, the ones that you've always used, to coming down to a concept of specific wires with specific properties that you know about that you will apply to overcome very specific problems. So we understand what task we're asking the wire to do. Is it penetration? Is it lesion tracking? Is it device delivery? We understand which wire has those properties based on its form, its makeup, its tip load, its coatings, etc., etc. And through that understanding, choosing the right wire for the right situation, we achieve success. Thank you.
Thank you very much, Alan. It's been a wonderful presentation and very, very clear. Once again, I would like to ask you a short question before moving to the next presentation. So just could you, I mean, we have very different features of every kind of wire that we have on the shelf. Maybe we can even know them theoretically. When, for example, we use a double coil technology, all the beautiful stuff, the engineeristic stuff that you've shown us, we can understand that you increase the surface of contact with the tip of your wire and you increase the precision. And maybe you can test it in tortoise vessels and so on. Which is your suggestion to be confident and to be familiar with the specific features of the wires that you have in your cat labs? I mean, how can you feel, can you give suggestions to the people to feel the difference between one and the other in order to know where to use it?
So you say, if I've understood the question correctly, you're asking, how do you get an idea of this ex vivo so that you can try out these wires? Yeah. So Asahi have got some fantastic models that you can use for testing out all the different wires. They're basically models where they've tried to recreate in vitro the complexities of CTO. So they're models that have tubes which go around lots of different bends. They will have CTO segments in them where they are full of like a gel-like material. In other segments, they put in a kind of gritty material into them so you can get an idea. And the beautiful thing about these is that you get a real understanding about steerability and understanding what you're looking at. So the funnest thing to watch people doing this is to watch them moving a wire through this, and they're watching it all on a big TV screen. And they're wondering why their wire isn't going any further. They're trying to turn it. They can see the tip moving. It's still not doing anything they want. And then you just point out to them gently that there's a second camera that's showing it from a completely different angle. And what looks like it's going right down the middle of a vessel in one angle is actually in a different angle going right into the wall and is clearly can't move because it's right up against the wall. So having a go on those types of models is a really great opportunity to try out these different things in practice. You can generally get access to them through your Asahi technicians. If you go to conferences like Europe PCR or MLCTO, they'll all have those sorts of practical stations there where you can give those a go, and I would highly recommend that.
Thank you very much. Thank you very much. So maybe we can move to the last presentation, which I'm gonna show in a second. Then we can move to the sorry, it's the wrong condivision once again. Okay, sorry. Okay, here we are. Everything's gets stuck, sorry. My computer is creating a problem, so I have to start the presentation again, but I'm ready to start now. So before moving, the next presentation will be about, okay, here we are. Next presentation will be about how to choose the wire in the correct situation, and how to try to create an algorithm, or to use an algorithm that we already have provided by the scientific data. I think that now you can see my screen. So we have different algorithms, more or less complex, or more or less whatever. We try to analyze how to treat a CTO PCI, and all of them relies a lot on the technical part of the technical part of you, more than choosing the correct kind of wire in order to do that. I mean, all of them moves from antegrade to, you have to go antegrade, you have to go retrograde, you have to go ADR, antegrade wire escalation, and so on. And irrespective of the kind of algorithm that you try to analyze, more or less they try to do the same. They try to show you how to move from one technique to the other in order to be successful at the end of your procedure. But what about wires? Nobody tells you how to try to select the wires. More or less, we are in the same situation that we had 10 years ago. This is what has been provided by the Dr. Wu, which is more or less what we had from the European perspective, the Japanese perspective, or maybe even the American perspective. So start from something which is soft, relatively atraumatic, tapered, with not a great penetration power, and then if you fail, move to something else which is probably more penetration power, stiffer, and so on. But this is not a clear algorithm in order to try to understand which wire to try to use. It was easier in the early days of our experience, because in these days we were very lucky, because we had techniques, we were exactly similar, exactly coincident with the wire that we choose. All we discussed about penetration and drilling in our CTO PCI, but what we didn't understand was that we were discussing about specific tools and specific wire. People who used to drill in order to try to cross the CTO used to use Miracle family and then UB3 family. People trying to use the penetration technique were using Conquest or something stiffer, Confianza wire in order to go there. But after that, after a few years, finally we were able to analyze a little bit better the composition of our CTO, and we were able to understand that all the CTO are not created equal, and the times makes a role in the evolution of the CTO. So when you are dealing with a CTO like this, we are in a situation like the one described by Mr. Faldo at the beginning of the presentation. Some microchannels, soft tissue, you can use something probably which is not so penetrative, and you have to have something which is able to do something different from what we have to do in the last in the dissection, when you have a lot of calcium, tough structure, bifurcation representation, and you have to be a little bit more aggressive in order to cross that. So we were able to understand that we needed something more than something able just to drill or to penetrate. And it was the concept of the antegrade loose tissue. So we wanted to have something, a wire which was a little bit stronger than the resistance into the CTO body, which is able somehow to create and to find the way of lower resistance into the CTO body in order to arrive at the end of our CTO. And so the sliding technique was described, and once again we're confusing a technique with a family of wires, which were the Fielder XT family, Fielder XT in the beginning, a Fielder XTA and Fielder XTR. So, which was something very tapered with polymeric coating, very able to be very slippery, and able to cross into the lesion, trying to find a way of minor resistance, moving away from the spot of calcium and moving away from the bigger point of resistance. And this is an example of we were able to do. This is a short, non-complex CTO PCI. You can see there is some tapering. That you can find that there is not a lot of calcium. So in this situation, the Fielder XT wire are still a very good way to solve the problem. You can put a micro, you just put the wire in front of the lesion, you start moving the wire, and the wire by itself is more or less able to find the better way to do that. And this is also shown by some old data, which show that the Fielder XT family wires are the preferred way to start the procedure in the majority of the procedure that we start. And also have a very high percentage of success if compared with other wires. But you have to realize that sliding is relatively safe. The major problem that you can create is create some dissection at the level of the proximal cap. Sometimes, very often, is effective, and sometimes you can have, surprisingly, the softer tip can penetrate more than the stiffer tip because it's able to slipper through the point of resistance instead of going and rushing through it and rushing through the wall. You have a better definition of the CTO composition, but it's completely uncontrolled. More or less, irrespective of what you pretend, the wire tends to do what she's able to do. You just push and try to follow with your hands the movement of the wire, which is able to advance by itself, and you have just to control that you're not going in a funny way and funny position or dangerous position. Drilling is more or less the same concept, is also uncontrolled, is safe, is also effective in clarifying the anatomy, and is still a role in a situation like this. When you don't know precisely in this kind of ostial lesion, ostial CTO of the RCA, you have a very long CTO, you don't see a lot of calcium, you don't have a lot of anatomical information. So if you put it inside a wire which is able to stay into the vessel wall without creating any damage, and without, at least in the worst scenario, going into the former subintimal space, but is not moving, not able to create a perforation or create a damage, then maybe you can clarify a little bit the anatomy of your situation, and in the worst situation, you can start considering moving to a reverse scar technique or something like that. But in this case, with the wire put in this position, you have definitely a better perception of the anatomy of the lesion itself. And so it's still the role of the drilling and the UB3 family for this kind of stuff. Stiff wire is still a role. The main feature is the fact that they have a very high penetration power. We have a poor tip control. They tend to go in linear progression, so they tend to go straight and are the most effective when we have to face with calcium. But as Alan used to say in the previous presentation, they are very poor in tortuous anatomy. As they tend to go straight, they tend to go straight if they have the calcium in front of them, if they have a band, or if they have whatever. So they are not very good when the anatomy is not very clear, and we have this kind of situation, which is a little bit of ambiguous. So what to do in cases like this? Now we have a situation which is a CTO which is not that long, not very clear in the beginning. You don't see the LAD, so you have to do your homework and to find if there are collaterals providing something good. And when you put the information that you look for the distal part of the vessel, you look at the proximal part of the vessel, you can start in a situation like this, maybe with something like Fielder XT family. If you see the tip of the microcatheter is at the level of the entry point, not a lot of calcium, not very long, tapered from the beginning, you can start from the XT. But the XT family, this was an XTA, sometimes tends to fail. They are not effective in 100% of the cases. So What can you do in this kind of situation? The filter XTA is definitely not in the right position. You can start drilling, you can use a stiffer wire, but once again, technology came in our help. So it was created a new family, a relatively new family of wire, which was able to deflect in front of resistance, and which is soft enough to be deflected when resistance was encountered, and with a good torque response, a torque response which is good enough to be very precise in the advancement. So you can advance the wire till you have the first deflection, redraw a little bit, redirect, try to solve the first problem, re-advance till you have a new deflection, then you can redirect till you reach the end of the CTO. Once again, we're talking about technique, but we're talking about a specific family of wire, which are the Gaia family. They are not so new. We're waiting for something new to be developed in the next few months. We're waiting for the next generation of this wonderful wire. But these wires were some sort of game changers in our CTO PCI. Three kinds of wires, different tip loads, different diameter, different the exit diameter at the end of the wire, which were able to solve different kind of problems. The pros were that the wonderful tip control, and the cons were that they were relatively poor when they were facing calcium and higher resistance. Another pro, and something that you have to realize with the wire, once again, is the case that we had before. These are very, very good wire because they are very precise. You can decide where to direct them, and you can be very, very precise in moving them. But to do that, you have to know where to direct them. I mean, you have to have a very precise target in order to have a major advantage in the utilization of this wire. They are not something magic that can go through all kind of anatomy, all kind of lesion, and if you go blindly, you lose 90% of the feature of the wire in something that, and with something that makes them very similar to the other wires. So they are very good in antegrade fashion, they are very good in retrograde fashion, but once again, you have to be able to have a clear target where to direct your wire in order to be very precise. Otherwise, you're just poking with the tip of your wire and just advancing it without having any kind of advantage with this wire. To solve this problem, there are specific anatomy when the anatomy is not very clear. We already thought that you can drill your wire and have some sort of advancing, creating some kind of space in the space of minor resistance. But once again, we have from the last couple of years, something which is able to solve this kind of situation. Drilling, when you have this kind of calcium and when the anatomy is not very clear, is not always a good indication. The probability of migrating in a space or in a place where you don't want to be is relatively higher, and the probability to be effective when you have all this kind of calcium is not that high. So if we move again to Alan's presentation, what you want to have is something which is not too penetrative enough to go through the lesion, but not enough to create harm, and something which is slippery enough to be able to cross the lesion and to be able to slip through the lesion itself. So once again, we have a new wire, which is, I have to admit, a game changer more than expected. I hadn't had a lot of expectation on this wire when came on the market, but now it's I use it in a very high percentage of my procedure. When I don't know the anatomy, when I have calcium, and when I want to try to clarify without trying to be too aggressive, I try to use this kind of wire before starting knuckling and migrating in other spaces. I can try to stay in the true lumen for a little bit more. You have a wire which is 3 gram, 0.14 inches, so it's not tapered. But the major advantage, if compared with, and the major difference, if we compare with the UB3 wire, is the fact that we have the engineeristic composition, which makes this kind of wire something brilliant, and also polymeric sleeves that covers the coils around the wire. So when you have a polymeric sleeve covering the coils, you reduces the surface of contact with the coils of the wire with the surface of the vessel, and this is one of the reasons why the wires tend to be more slippery and can advance a little bit more. We have them in pre-shape. It's 3 gram as a tip load, as a torque response, which is very comparable to all the torque response of the dual core technology that we already know from many wires from Asahi. And you can see that when you check for the tip, the control of the movement of the tip of your wire, you're definitely more precise, and you have definitely a lower whip motion if compared with other situations, like you can see on the right part of the screen. And you can see that more or less the transition is very smooth, while the other wire which don't have this kind of technology tend to have a whip motion and move abruptly from immediately from one angle to the other. Also, the rigidity of the tip is different, but is very specific, and it's very engineeristic, so makes a little bit less difference in the practical, in the immediate perception that you have. And also the support of the shaft is very well balanced, so you have that you don't have abrupt transition from the tip of from the proximal to the distal part of the wires. You don't tend to lose the support moving straightly towards the end of your wire. So if we move again to the case, you can see how easily the wire tends to go into the CTO body. You can see that the force applied both to the guiding catheter, both to the microcatheter, is not too higher, and despite of the fact that of course you have to push somehow, you see that the wire is able to cross into the calcific part of the lesion, reach the distal part, and maybe at that point you can start of thinking of being effective and move it to the next step of the problem, which is advancing the microcatheter and finishing the CTO PCI. Let's say that when you talk about algorithm in choosing the wires, my personal point of view is that there is not a clear algorithm in order to use it. Every wire is able to solve one kind of problem. So you have to analyze which kind of problem you're expecting to face during your CTO PCI. And so you have to analyze carefully all the images and the data that you have from your angio, CT scan, IBUS, or all the images that you have when you start the procedure. So as was said before, you have to analyze the entry point. You have to try from the fact that it's tapered or not, ambiguous or not, you can guess if it's softer or a little bit more stiffer. You can analyze the calcification. You can analyze if the course of the vessel is clear or not. So if you need something to clarify the course of the vessel, or if you can just thinking of going straight and follow the path that you have in mind. You can understand the length of the occlusion, and you can see all the information, which are probably the most important fact in order to choose the wire, rather than choosing a wire according to subsequential algorithms. Start from this, move to that one, and then move to the third one if the previous two fails. If you compare with JCTO score from the angio, you have also some other information, which is all the stuff about the distal portion of the CTO, which is not so described in the JCTO score as previously described. So, a couple of examples in order to analyze the situation. In this kind of situation, we had poor ejection fraction, LAD occlusion, quite calcified. The cap is not very clear. Maybe there is some tapering, but the better analysis, it was and not a blunt occlusion at this level, with some collateral coming from the right from an apical point of view. So in the hypothesis that there was some tapering, you can start trying with a softer wire and try to follow the path. It was not possible to make the puncture neither with the Filderixty family, neither with the Gaia family. So in this kind of situation, you're not following an algorithmic, but you understand that the main problem at this point is the calcium, and so you have to move to a wire which is definitely stiffer. And with this was the puncture was performed with a Confianza Pro 12, which went, as you see, was able to enter into the calcium and was able to advance a little bit straight into the LAD. It was not possible to advance the micro into the CTO body and to exchange the wire to another wire. So I decided to go to a retrograde from this kind of collaterals. Now you have to understand which kind of features you want to have from your retrograde wire. So in this kind of situation, you have a collateral which is epicardial, so you have to be safe. You have to understand the size of the epicardial, of the collateral. You have to understand if there are a lot of bending, how many bends there are, the size, the diameter, and all this kind of stuff. And so probably it was possible to advance a wire into this kind of collateral very effectively, but mostly very safely. And this was related to the fact that also for retrograde wiring, we have specific wires which are with even more engineeristic evolution that were from what we've seen in the antegrade part of the wire that I was describing. You see that there is still the same concept of dual core shape. This is a shaping ribbon, perfectly a shaping ribbon wire. It's a dual coil, but also the rope coil is made not just by a single wire looping around the wire, but several wires looping around each other and then looping around the wire itself, which makes the wire definitely softer, definitely more atraumatic. And the main reason is the fact that if you think of this point about a single wire, you have some kind of rigidity. If you think about this space, about 4 different single wires, you have some more free space inside, which makes the coils a little bit more able to be flexible and to follow. The wire is 0.3 gram and is 0.014 inches as a tip, and it is pre-shaped. And one of the most important features of the wire is the fact that it's pre-shaped, and you cannot shape in a different way than what is provided by the company without losing the features of the wire. After that, it was possible to advance the micro. Also by the micro, there is a lot to say, but once again, there is not one specific algorithm to follow, but you have to choose your micros according to the features of the lesion that you're treating. It was possible to advance, and then it was possible to make the reconnection. In this specific case, it was made with a Gladius because I was a little bit scared cared about the calcium in the proximal part, but there is no harm at all in using a Gaia family, because in this specific case, even from retrograde perception, you have a clear target provided by the antegrade wire and the antegrade balloon. So it is possible to use both of the kind of wire in this situation. Maybe filler XT is not a good option because of the fact that you have all the resistance of the calcium here. You see that the calcium is important, the indentation in the balloon. With the child in mother, it was possible to advance the wire into the child in mother, and then with a shockwave, it was possible to win the calcium and gain a good final result. Once again, different scenario. Once again, we are dealing with an LAD, and we are dealing with a collateral which is completely different from the previous one. We have several septal, very tiny, and with severe bending in the transition zone from the PDA to the septum, from the true septum. So according to what we said up to now, the first wire to choose could be the SUO03, but the SUO03 gets stuck into the septum, because one of the main features of the wire, I see it's very atraumatic, it's very safe, but the bend of the tip is fixed. So when you have to shape your wire according to very severe bending, somehow you cannot do that. And when you want to have a 90-degree bend on the tip of the wire, you cannot obtain from this specific wire. But it's something that you can obtain, for example, from this specific wire. Once again, it's definitely less sexy. If you just look at the engineeristic point of view, it's definitely less complex than the SUO, more complex than most of the wire that we have on the shelf, but less complex than the SUO, just a double coil, 0.015, 0.8 gram with a polymeric in coating, but it's not pre-shaped. And the fact that it's core to tip wire, you can shape wherever you want, very close to the tip or a little bit more distal from the tip. In this case, it was pre-shaped very, very close to the tip with a 90-degree angle. And it was possible to advance the Sion black into the septal in completely a different position, which was possible to gain with the SUO03. You can see that the fact that the wire is slippery and the polymeric coating reduces the friction and allows you to advance with less friction than other wires. Then it was possible to put the wire into the distal LAD, advance the micro, and once the micro was advanced, it was possible only to obtain this kind of tip injection. So it was very, very difficult to deflect any kind of wire into the proximal LAD. If you use a Gaia wire, probably you will create a dissection here, and more or less you can obtain the same result if you use directly a Confianza or a Gaia family or something like the Gladius and so on. So in this case, it was possible to use a softer wire, not dedicated CTO wire, which was the regular Sion. Once again, a non-CTO wire into this situation, because if you look at the image, it is not very calcified. The only problem is just that it's very close to the emergency of the septal. So you want to have something which is not so penetrative, but which you are able to control and to direct wherever you want according to your will. Then it was possible to advance the micro. And once again, we are facing in a situation where you can advance a wire directly toward a clear target. And so you can use a Gaia family wire, or you can use, for example, once again, a Gladius. There is no harm to use a Gladius in this kind of tract. In the better scenario, you can achieve true and direct retrograde crossing. In the worst one, you can achieve success with a reverse cart, and at the end of the day, there is no difference at all in the outcome for the patient and in the outcome for the result. So it was possible to advance. Once again, it was needed to advance a dual lumen catheter in order to gain the distal portion of the LAD. And once again, Sion wire was able to be advanced into the lesion, despite of the fact that there was some disease at this portion of the bifurcation of the septal, and then the good result was obtained. So my take-home messages are that you have to know the features of your wires. You cannot try to use to start a program of conventional PCI and of course of CTO PCI without knowing the gears and the stuff that you're using, because every kind of features and all the features that are written on the papers that are provided with the wires changes the behavior of the wire in a specific condition. And so it's very important that you're familiar not just with the theoretical part, but also with the practical reaction, maybe using simulators and all that kind of stuff that we already discussed. Then don't move according to the latest wire that has come on the market. You're not a more brilliant operator if you're able to use the newest and maybe the more expensive wire that you have on your shelf, but you have to use the wire that is able to solve the specific problem that you're facing in this specific moment. So you have to analyze the reason why you are failing, or the problems that you can encounter when you start the procedure, or the reason why you're failing, and then move to the choice of the wire according not to a specific algorithm, but in order to do something that is able to solve the problem. And then you can define your own algorithm and define that maybe this kind of wire, the Gaia wire, is very good when I know where to go, and other wires are a little bit better when there is a little bit more calcium and so on. But then you're moving not according to a specific algorithm, but in order to try to solve the problems that you're facing and you're encountering. So thank you very much. And so I can stop the sharing of my screen. Okay, here we are. So, okay, I've done it. So we wait for your questions, and we wait for all your comments in the question and answer part of the screen. There are already some messages, and then maybe we can start from that. But what are your perception about what we've said up to now? So do you have any comments? Do you have any ideas about you don't agree with something?
No real comments. It was an amazing presentation. Thank you, Dr. Gagnon. For me, just one question. When you are in dissection in a suboptimal space, which is your favorite wire to re-enter? Gaia 3 or more with a T-flow more higher, like a Confianza? What is your experience?
Once again, it depends in which kind of scenario you are. You are in the subintermal space,
Yeah.
then you can decide to move, for example, to retrograde approach, and then move to retrograde card, to reverse card.
Yeah.
And then, so in that case, probably I can use something like Gaia second in order to be redirected, or something polymeric like Gladius. If I want to re-enter from the integrate approach into the distant lumen, maybe I can use a stiffer wire, Confianza Pro 12, maybe even something like something different, but something very stiff and something very penetrating.
For the puncture.
So we have some questions from the people with us in this meeting, and first of all, there is a concern about the clinical indication. So Alan, I leave you the difficult stuff. The question says the ischemia trial showed no benefit for treating nuclear ischemia in asymptomatic patients. So how can we justify the fact that we still treat asymptomatic patients?
That's a great question, and I think it's one that we're all increasingly wrestling with. The results of the ischemia trial, I don't think really accorded with where we had our heads at around 10 years ago. We believe that more ischemia would be associated with poorer outcomes, because that's what a lot of previous registry types of studies had shown us. So I think there's some things we need to sort out within this and unpick within this answer, though. So firstly, do I generally treat patients with CTOs who don't have symptoms? Answer, in general, no. Why? Because PCI in stable coronary disease, its greatest benefit to my eye is improving symptoms. So if you don't have any symptoms, it's difficult to see an improvement. However, if you have patients who have got demonstrably large areas of ischemia, but tell you that they're asymptomatic, I think it's all about how you really judge if they're asymptomatic. If I have a pair of shoes that are too small for me and I go out for a walk, they hurt. And pretty soon I'll stop going out walking. And then they don't hurt anymore because I stopped wearing the shoes. So if a patient is asymptomatic, I think you really have to understand if they're asymptomatic because they've changed their lifestyle to accommodate their symptoms, or are they somebody who could be doing more than they currently are, but are not because they would get symptoms if they did that thing. So you might want to try and do some exercise testing or things like that to see whether people truly are asymptomatic. I think with large volumes of ischemia, and particularly in proximal vessels as well, I think some of us are still nervous as to generalizing the results of the ischemia trial to say that it's the wrong thing to do to use angioplasty. And remember, the ischemia trial wasn't just about, is it wrong to treat people with stents? It was about what's the best first option. Is it a reasonable first option to go with medical therapy? Or should we be using stents as well? And I think it does still stand that you have, the more ischemia you have, the more risk you are to have spontaneous MI, and that the rates of spontaneous MI seem to get better with patients who had PCI later on. So I think it's still a difficult area. I rarely do patients who don't have symptoms anymore. And I would worry about how I was kind of coming to know that they had large amounts of ischemia if they were asymptomatic. Why was I testing them in the first place?
Well, thank you. It was a beautiful answer. So when to use, another question is about when to use the Gladius X and typical cases and so on. For me, this is the typical wire when you would want to stay into the vessel wall, somehow into the vessel architecture. You want to advance in a fast and effective way, but also in a safe way. You want to clarify the anatomy, and you want to try to avoid the calcium turning around it. So for me, it's a long occlusion, not very clear path, and I want to try to clarify the anatomy before and trying to advance somehow my gears in a safe way. Any other ideas for you? Any other comments?
I think that really covers it. I mean, I think what you really highlighted very well in your talk was that there are some times where you have, there's always going to be ambiguity of anatomy in an occlusion segment, but your likelihood in a very short segment of there being lots of bends between where you're starting from and where you're getting to is very low. And in a long segment, it's very likely that you've got lots of bends, so which you will have no idea where they are. And when you have long segment occlusions, you want to be able to get across those occlusions safely, number one, and efficiently. And when you don't know where you're going, it's very difficult to be safe. But there are techniques that you can use. So most people will have heard of knuckle wiring, and that's essentially where you take a wire and you bend it over. So instead of all your tip force coming through the single point here, it's suddenly that tip force is all dissipated over a much larger area. And that stops you ripping through a vessel and puncturing through a vessel. So if you push a wire on a knuckle, the tip force that's there is not sufficient for it to go outside of the architecture of the vessel. It can move within the architecture of the vessel, whether that's within the occluded lumen or whether you're in the subintimal space, but it shouldn't exit the vessel. So it's a way of being able to push in a very sort of blunt, literally push like that, and it will follow whichever way the vessel goes. And that allows you to reach the distal cap. And it's there where you want to invest your time in being able to look at methods for re-entry, whether that's with reverse cart coming at it from both directions, or whether that is an antegrade dissection re-entry technique. So the Gladius is a bit like that in that the tip load that it has is generally not sufficient to be able to puncture out of the vessel. But you have to make sure that you are still paying attention, because knuckle wires, Gladius wires, any wires can also go out into small side branches and stuff and then perforate out at the end of those. So they allow you to achieve crossing of ambiguous anatomy safely, but that doesn't mean you can't take your eye off the ball.
Yeah. So the reason, so let's say Gladius X could be the step before starting knuckling, could be. And the reason, just to answer the question, the reason why the wire is safe is the fact that is not even with 3 grams quite far from the tip of the microcatheter, you're not able to go outside of the vessel. You can perforate a smaller vessel if you go in a small branch and so on, but you have not the power to exit from the vessel if you compare with 3 grams with maybe the Confianza Pro 12 or the 20 or whatever. So this is the reason why it's safe. A question that I would like to ask to both of you: do you really feel any difference in knuckling with the Gladius X and the Gladius MG? Do you really feel that there is a major difference and you choose one or the other? I mean, if you are going with the Gladius X and you start in the wire tends to start knuckling, you move to the Gladius MG, or you start knuckling the Gladius X?
I would just carry on. Usually at that point, if I've made a decision to commit to knuckling, I'm just going to push it and let it go. I think the design of the Gladius MG was to make a relatively tight knuckle, but with more push force. When we were using other types of polymer jacketed wires, like a Pilot 200, they tended to form a larger knuckle. And when you have a larger knuckle, it creates a bigger subintimal dissection. And that can mean that your re-entry devices have a bigger challenge on their hands, and you as an operator have a bigger challenge trying to prevent the formation of subintimal hematoma, which can squash the lumen that you're trying to get back into. So, but honestly, if I was in that situation and had an EX and it started to knuckle and I made a commitment to knuckling at that point, yeah, I'm just carrying on. That to me wouldn't be a value proposition, that they would be so significantly different that I would think, I must stop now and go with a different knuckle.
So just a couple of answers before asking me as a last question. First of all, difference between samurai wire and the coating of Sion. Do you really feel any difference? Do you have the perception that they are different in terms of torque control or not? From my point of view, there is some difference, and the kind of feeling, the kind of control that you have the Sion is still not reached by other technology, engineeristic technology developed by other companies. But this is a personal view and a personal perception. What about your ideas?
I'll take that one. We don't have samurai wire on our shelves, so I don't know.
Okay, so let's ask. We won't talk about the microcatheter because it's out of the topic. But once again, the concept is the same. Know the features and use them according to the problems that you're facing. What about non-PCI vessel very calcified? So there is still some role for polymer. The polymeric wire is still the only solution, or the fact that you have a different wire, for example, Sion blue, and so on, can make any difference even in this kind of scenario. You can control them better, so you are able to cross even when the vessel is very, very calcified.
Yeah, I think that's one of those interesting situations where, in general, I would say that crossing calcified lesions is a lot easier than crossing CTOs. So it's generally not something I've invested as much sort of time and thought about to try lots of different wires in it. Definitely things that have got polymer jackets on perform a lot better when things get gritty, not surprisingly. But it's about understanding what the particular issue is again. So it's looking at what's happened. Is it that it's calcified, or is it that it's calcified and tortuous? Is it because the lesion itself is super tight, or is it that your just wire's been directed away from the lumen that you want to go for? So I think you have to understand the problem that you're dealing with, and that's a question of feel. It's also a question of paying close attention to what's happening to your wire tip. What's it doing? Is it bending over? How is it bending over? Where are the angles? Do you need to look in a different projection to see truly what the anatomy you're trying to cover is? Because it might be that the view that you're in at any one particular time could be foreshortening things, so that you don't necessarily understand the path of the vessel well enough to be able to steer properly.
So last question to Mr. Falteau, and then we can move to the conclusion. How difficult has it been to convince the medical staff to have the general preparation of the case with all the staff, the paramedics and so on, and which is the main value during the procedure according to you?
At the beginning of your program, the most difficulty is to convince. Okay, why do we need to spend 2 hours for an artery which is closed? What is the problem? There is no muscle. So that is in fact the first difficulty. But then when you follow up your patient and you see them 1 year later, yes, it's better for me. I have less dyspnea. It was a good idea. Thanks doctors. So you have it's something. It's a value for you. And then when you master the CTO program, you are going to master your daily complex PCI, because you are going to increase your knowledge in the microcatheter, the different wires you need. Your wires that you used in the CTO, you are going to use them in your daily complex PCI. When you have a calcification, you need, you have to try the Gaia third. Try it, and then you are going to improve your knowledge and to achieve the success of your PCI. That is for me the most value I have in the CTO, but it's something different like the other lesions. That's why you have to convince all the team, the medical teams, but also the paramedical teams, because it must be a whole team to achieve the success.
Yeah, I think that's a really great answer, because what we're doing here is treating patients. Okay, and every patient has their own individual need, and our job is to meet that need for them. So we're not there just to treat easy stuff. Yeah. We're there to make a patient have less angina and being able to live the life that they want to live. And if that involves doing complex PCI to achieve that, great, as long as it achieves it and as long as it produces the results that we want to, and it's safe enough to do that. So it's nice to do easy things. It kind of feels easy, but at the same time, that doesn't help those patients who don't have an easy solution. And finally, I would agree entirely. I use CTO PCI techniques in pretty much every case I do, because I'm always thinking about guide support, backup, wire selection, tool choices, etc. Anybody who's found any difficulty in delivering a stent in any situation, if you've learned CTO PCI, you'll go, I know, I've got an algorithm for this. This is what I do. And you just work through your algorithms and solutions happen.
Okay, thank you very much, Ben. Then probably it's time to close. We've reached our time and our goal. I would like to thank you for participating and for being part of active part of the meeting. And let me thank also Asahi for first of all for hosting this scientific and interesting part of technical discussion and scientific discussion, but also for making our job definitely easier and definitely more exciting. I mean, all the people who started from the beginning can understand how the game has been changed by this kind of devices, and by how the fact that we're dealing with wires were definitely more complex with specific features and so on, has changed our perception even in conventional PCI and in non-PCI patients. So it's been definitely a game changer. It's made our job definitely more interesting, and we have learned a lot from them, and so it's one of the reasons to thank them. Thank you very much, and see you next time. Bye bye.
Thank you very much for this great webinar.
Thank you.